Assalamu alaikum girls. It's second lecture, live lecture with you, and today we will discuss the junction FET. This is the 6.2 article of BG's treatment book. And here, first of all, please look at your book and see that how PN junction is being drawn. You know, whenever a P type material is brought near to N type material, a depletion region is formed. So, as there are P and P junction, so there are two depletion region. And in a junction FET, the voltage variable depletion region width of a junction is used to the effective cross-sectional area of a conducting channel. It means that when you will combine and make a FET by P and P, then a conducting channel will be formed. And that conducting channel will be in the center. Now figure 6.3a show that we have defined three regions here. Number one, we have defined a source, which is represented by S, then drain, which is represented by D, and at the center, we have gate G. The current ID flow through an N-type channel between the two P-type regions. It means the N region between two P regions formed a conducting channel. A reverse bias between these two P regions and the channel causes the depletion region to intrude into the N material, and therefore the effective width of channel can be reduced. Since you have fixed the resistivity of the channel by doping, the channel resistance varies with the change in the cross-sectional area. It means your variable depletion region serve as two doors of a gate which open and close on the conduction channel. In figure 6.3, electrons in the N-type channel drift from left to right, that is opposite to the current flow. The end of channel from which the electron flow is called the source, and end toward which they flow is called the drain, and the P plus regions are called gates. It means source and drain both are on the N channel. If the channel were P-type, then the holes would flow from source to drain in the same direction as the current flow, because you know that we take the conventional current which is due to the flow of the positive charges, and the gate region would be N plus when hole will be flowing. It is common practice to connect the two gate region electrically. Therefore, the voltage Vg refer to potential from each gate region D to the source S. Since the conductivity of the heavily doped P positive region is high, we assume that potential is uniform throughout the gate. In the lightly doped channel, however, the potential vary with the position. That is, in the heavily doped P plus regions, which are gate, it is constant, but for the lightly doped N region, it varies from position. It means we can consider channel as a distributed resistor carrying a current I. And it is very clear that the voltage from the drain end of a channel D to the source electrode C must be greater than the voltage from point near to the source end of C, source end of S. For low values of current, we can assume a linear variation of voltage Vx in the channel, varying from the Vd at the drain end to 0 at the source end. If you please look at the figure 6.3b, you can just see that we have attached the PNP FET with a battery in such a way that current ID is flowing through it. And if we plot variation of the displacement with the variation of potential drop, that we can see that we can get a linear relationship. As the distance vary from the source, as the distance from source increases, the potential drop also increases, which is shown by the graph. Now, whenever we will consider the function of any transistor, whether it is FET or BJT, the basic purpose is that how we can use it to switch on certain circuit or switch off the certain circuit. So, the next topic which we have to study is pinch off and saturation. If we consider N channel in simplified way by assuming that is there is no potential drop between the source and drain electrodes and as well as the respective end of the channel. So that if we assume that the potential drop at the drain end of a channel is the same as the potential drop across the electrode D. This is a very good approximation if the source and drain regions are relatively large, so that there is little resistance between the end of a channels and the electrodes. That is, if we make the source and drain regions relatively large, so there will be very little resistance between the end of the channels and the electrodes. Now, the figure at page 6.4. If we look at this figure, the gates are short circuited to the source, that is Vg is equal to 0, such that potential at X is same as the potential everywhere in the gate region. That is, potential remains same in all the gate region. For very small currents, the width of depletion region are close to the equilibrium values. As the current ID is increased, but when we want to increase the ID, it becomes important that the Vx is large near the drain end and small near the source end of a channel, because if we want to increase the current, then of course the voltage drop should be large near the drain end and small than the source end to facilitate the current flow. Since the reverse bias across each point in the gate to channel junction is simply Vx, when Vg is equal to 0, we can estimate the shape of the depletion region as in figure 6.4b. The reverse bias is relatively large in the drain and decreases towards 0 near the source end. As the result, the depletion region intrudes into the channel near the drain and effective channel area is restricted. So if you please look closely at the figure 6.4a and 6.4b, you can see that initially the electron flow and current are in opposite direction, and there is as you increase the drain voltage, current is also increasing. But when drain voltage is more increased, it means it more made more negative, then electron will unable to reach to the drain, and you will see that due to this reverse bias, the depletion region will become conducting region will become narrow near the drain end. Means depletion region increase near the drain end, and at this point you will see that the current will stop increasing with the increase of voltage. And at a certain voltage, reverse voltage, the drain region is totally cut off from the conducting region, and current just level off. That is, now with increase in drain voltage, there is no further increase in drain current. And this whole procedure is explained in the figure 6.4c, and this is known as the pinch-off channel. Since the resistance of constructed channel is higher, the IV plots from the channel begin to depart from the straight line that was valid for low current levels. As the voltage VD and current ID increase still further, the channel near the drain becomes more constricted by the depletion region, and channel resistance continues to increase. As VD is more increased, there must be some bias voltage at the depletion region meet near at the drain and essentially pinch off the channel. When this happens, the current ID cannot increase significantly with further increase in drain voltage. Beyond pinch off, the current is saturated and approximately at its value at pinch off. And once the electrons from the channel enter the electric field of the depletion region, they sweep through and ultimately flow through the positive drain contact. After the current saturates beyond pinch off, the differential channel resistance becomes very high. To a very good approximation, we can calculate the current at the critical pinch-off voltage, and we assume that there is no further increase in current as we increase VD. Okay girls, at this today I came to end of my lecture which I have to give you, but the actual thing which you have to do with these lectures, that you please concentrate on the figures as well and see that what is the reason behind all these things. And if you can't understand anything, you can just send me an SMS or ask in Google class that what is the purpose of it. What I expect from you girls, that please just draw these figures and understand that how pinch off is taking place. Now you are open for questions. You can record your questions and I will answer those questions accordingly.